Hello and welcome to Chromatogram Interpretation and Quantitation. This is the capstone where we bring everything together from the previous 4 lectures and apply it to the practical tasks of reading chromatograms, diagnosing problems, and quantifying analytes. By the end of this lecture, you should be able to identify all key peak parameters from a chromatogram, reading chromatograms, identifying problems, then the next 2 are quantitative, turning peak areas into concentrations and verifying system performance, and the last 2 are synthetic, method development and regulatory interpretation. There are 4 worked examples distributed throughout. We begin with the chromatogram anatomy, then devote significant time to comprehensive review of peak-shaped problems, tealing and fronting, with the root causes and solutions. Then we cover integration, quantitation methods, system suitability, and method development. It's the most practically oriented lecture in this module. We're reading a chromatogram. This is a realistic HPLC chromatogram showing all the features you need to be able to identify. Starting from the left, the injection disturbance at time 0 is caused by the sample solvent passing through the detector. The void peak at Tm marks the dead time. Peak 1 is a well-shaped Gaussian peak. Peak 2 is the main analyte. Note it is the tallest peak, typical for an API acid. The small peak at 12 minutes is an impurity. Peak 4 at 16.5 minutes is broad, suggesting it has a high retention factor. The baseline shows a slight drift upwards, which could indicate a column bleed, mobile phase composition change, or temperature variation. In a real lab, you need to extract several parameters from each peak: retention time, peak height, peak area, base width, half height width, and asymmetry factor. The data system does most of this automatically, but you need to verify the integration and understand what each parameter means. Peak tailing is the most common chromatographic problem. The diagram shows a tailing peak in red compared to an ideal Gaussian dashed in gray. The front edge is sharp, but the back edge decays slowly. The tailing factor TF is measured at 5% of the peak height. It is the total width W at 5% divided by twice the front half width F. A perfectly symmetric peak gives TF of 1.0. USP requires TF of 2.0 or less. The most frequent cause of tailing in HPLC is secondary interaction between basic analytes and residual silanol groups on the silica surface. These silanols are acidic and can ionically bind basic nitrogen-containing compounds. Solutions include using an end-capped column where the residual silanols are chemically blocked, lowering the pH to protonate the silanols and reduce their acidity, or adding a competing amine like triethylamine to the mobile phase. Column degradation can also cause tailing. If a void forms at the head of the column, the band broadens asymmetrically. Extra column dead volume from poorly connected fittings adds band broadening that manifests as tailing. The block at the bottom explains why tailing matters. It degrades resolution, sensitivity, and integration accuracy. In regulated laboratories, excessive tailing causes system suitability failure. Peak fronting. Peak fronting is the mirror image of tailing. The front edge of the peak is gradual and the back edge is sharp. The tailing factor is less than 1.0. The most common cause is column overload. When you inject too much sample, the stationary phase becomes saturated and the isotherm becomes nonlinear. The excess analyte cannot partition into the stationary phase and instead runs ahead with the mobile phase, creating the characteristic front shoulder. The fix is simple: reduce the injection volume or dilute the sample. The diagnostic test described in the red box is invaluable. Inject at half concentration. If the peak becomes symmetric, you have confirmed overload. If it remains fronting regardless of concentration, you have a column problem, usually a channel or void in the packing bed, which requires column replacement. Solvent mismatch is another common fit cause. If the sample is dissolved in a solvent much stronger than the mobile phase, the analyte band spreads at the point of injection before refocusing, creating a front shoulder. The solution is to dissolve the sample in mobile phase or a weaker solvent. Troubleshooting gallery. Common chromatographic problems. This troubleshooting table is one of the most practically useful resources in this entire module. I recommend saving or printing the slide for laboratory reference. Each row describes a symptom, what it looks like, the most likely cause, and the corrective action. The troubleshooting strategy at the bottom is the logical approach. First, run a blank to determine if the problem is in the system or the sample, then run a standard to confirm the system is working, then change one variable at a time to isolate the cause. Never change 2 things simultaneously. You will not know which change fixed the problem. Common pitfalls. Ghost peaks often come from contaminated mobile phase or carryover in the auto sample. Negative peaks are almost always caused by refractive index mismatch when using an RI detector, or when the sample solvent has different UV absorbance than the mobile phase. Retention time drift usually indicates the mobile phase composition is changing, either through evaporation or through gradual degradation. Peak integration. Getting accurate areas. Integration, converting a peak on the chromatogram into a number, is the step that turns separation into quantitation. Modern data systems do this automatically, but you must understand the methods and verify the results. Perpendicular drop is the standard. A vertical line is drawn from the valley between two partially resolved peaks down to the baseline. Valley-to-valley integration treats the valley as the boundary between the peaks. Tangent skim is used when a small peak rides on the tail of a large one. A tangent line is drawn from the back of the large peak, and the small peak is integrated above this line. The red box contains a critical warning. In regulated industries, changing integration parameters to manipulate results is considered data integrity fraud. The FDA has issued warning letters and shut down facilities for this practice. Integration parameters must be set before the analysis begins and justified in the method. The comparison table between peak area and peak height is important. Area is the standard for most quantitative work because it is less sensitive to flow rate variations. Height is sometimes preferred for very noisy baselines or when detecting the trace impurities near the detection limit. Let's do our worked example. Remember to pause and try it beforehand before we go through it together. This worked example demonstrates internal standard quantitation using a real-world application, caffeine in an energy drink. The internal standard, 7-chlorotheophylline, is structurally similar to caffeine and chromatographically well resolved from it. It is added at the same concentration to all standards and samples. We use the response ratio. The area of caffeine is divided by the area of caffeine is divided by the area of the internal standard. Instead of the absolute caffeine area, this ratio is independent of injection volume variations, which makes the method more robust. The calibration is beautifully linear with the R-squared value of 0.9999. The sample gives a response ratio of 3.45, which corresponds to 82.1 milligrams per liter in the diluted solution. Accounting for the 50-fold dilution, the original energy drink contains 4.1 grams per liter of caffeine. The block at the bottom explains why internal standard methods are preferred for complex matrices. The internal standard measure experiences the same losses and variations as the analyte, so the ratio self-corrects. Second worked example, again, try this on your own before we go through. This worked example shows how pharmaceutical impurity profiling works in practice. The method uses area percent normalization. Each peak's area is divided by the total area of all peaks. This assumes equal response factors at the detection wavelength, which is a responsible and reasonable approximation for structurally related impurities at the same wavelength. The results table shows the API at 99.52% with 3 impurities. ICH guidelines, Q3A and Q3B, define action thresholds based on the impurity level. Below 0.05%, you do not even need to report it. Between 0.05 and 0.1%, you must report the level. Between 0.1 and 0.15%, you must identify the impurity structurally. Above 0.15%, you must qualify it, meaning you need toxicological safety data to demonstrate the impurity is safe at that level. In this example, impurities A and B exceed the identification threshold, so they need to be structurally identified, typically by LCMS. Impurity C is above reporting, but below identification, which this type of analysis is performed on every batch of drug substance manufactured worldwide, and the chromatographic method must be validated to detect impurities at these extremely low levels. Our third worked example. Again, pause and try it yourself before we do it together. This example shows the replicate precision component of system suitability. 6 injections of the same solution give area and retention time data from which we calculate the percent relative standard deviation. The area RSD of 0.23% tells us the autosampler is injecting reproducible volumes and the detector response is stable. The retention time RSD of 0.12% tells us the pump is delivering constant flow and the column is well equilibrated. Both values are well below the USP limit of 1.0%. These calculations, combined with the resolution, plate count, and tailing factor, are covered in the HPLC lecture. Form the complete system suitability package that must pass before a sample is analyzed. Method development, a systematic workflow. Method development follows a systematic 6-step workflow. Step 1 is defining the goal. What are you trying to measure? In what matrix, at what precision, and under what regulatory framework? This determines everything that follows. Step 2 is scouting. Start with the generic C18 column, acetonitrile water gradient from 5 to 95%, B over 30 minutes. This wide gradient reveals where your analytes elute and whether the column chemistry provides any selectivity. Step 3 is the most critical, optimize selectivity. This is where you try different columns, different organic modifiers, different pH values. Remember from the fundamentals lecture, selectivity is the most powerful lever. Target RS of at least 2.0 for the critical pair, not just 1.5 to build in robustness. Step 4 is fine-tuning. Adjust the gradient or isocratic composition to place all analytes in the K equals 2 to 10 range. Set the detection wavelength at the analyte's absorption maximum. Step 5 is formal validation per ICH Q2R1, specificity, linearity, accuracy, precision, LOD, LOQ, robustness, and range. Step 6 is routine use with ongoing monitoring. The dashed feedback arrow shows that if optimization fails, you may need to return to scouting with a completely different column chemistry. Worked example, method development. Again, pause and try it yourself before we go through it together. This worked example walks through a complete method development from start to finish. The goal is straightforward. Assay 2 APIs simultaneously with baseline resolution in under 10 minutes. The scouting gradient on C18 shows both analytes are well separated with resolution greater than 5, which tells us the column chemistry provides good selectivity and we should try isocratic to simplify the method. Testing 3 isocratic compositions reveals the trade-off. Lower organic gives higher K values and better resolution with longer runtimes. At 10% acetonitrile, K2 is 12, which is too high. At 20%, K1 is only 1.5, which is borderline. At 15%, both K values fall in the 2 to 10 sweet spot, with excellent resolution of 4.5. The final method is simple and robust. Notice that we did not need to change the column or the pH. The default C18 with phosphoric acid buffer provided sufficient selectivity from the start. The SST results all pass comfortably. This sample illustrates that many pharmaceutical assay methods are surprisingly simple once you follow the systematic workflow. Module summary, key takeaways. 7 takeaways to close the module. First, never trust automated integration without visual verification. Second, know the difference between tailing and fronting and their root causes. Third, the dilution test is your best diagnostic tool for fronting. Fourth, choose the right quantitation method for your situation. Fifth, system suitability is non-negotiable. Sixth, method development is systematic, not trial error. Seventh, ICH thresholds define your regulatory obligations for impurity reporting. This concludes the chromatography module. You now have the theoretical foundation, the instrument-specific knowledge, and the practical skills to work with chromatographic data in any analytical laboratory. The next module will cover mass spectrometry and NMR spectroscopy, techniques that are increasingly coupled with chromatography for identification and structural confirmation. Here are your practice problems. Make sure to work through them. Solutions will be posted. If you have any questions, please let me know.